Alright, hi everyone, my name is Paul Yu. I'm going to be teaching Chapter 5, Section 1 of Statistics, which is probability distributions. So you might be asking, what is a probability distribution? A probability distribution is a way to describe the probability of a random variable. And a random variable is a single number variable determined by random. So it's usually determined by the letter x, as shown here. And there are two different types of random variables, one being the discrete random variable and one being the continuous random variable. The discrete random variable has a finite amount of values and the value collection is countable. So like this can be two coin tosses, and you can count how many times you get heads and you can count how many times you get tails. So let's just make it up. Out of 2 coins, you get 1 head and 1 tail. A continuous random variable has an infinite amount of values and a value collection that is not countable. So this would be like the time for a Windows update or a Mac update. You know, those computer updates take forever. Computer update. Not countable. And then there are 3 requirements of a probability distribution. The first one, a numerical random variable with number of values tied to corresponding probabilities. The second, the summation of probabilities equal to 1, but 0.999 and 1.001 are okay because of rounding errors. 3, the probability of each random variable x is between 0 and 1, but they can be also equal to 0 and 1. So let's go over this example. This first example is you toss 2 coins. Did I say that right? 2 coins, yes, into the you just toss 2 coins with the probability of getting heads. What are the probability? So I have this data table right here on the left. This data table. One side being the x, and then the right side being the p of x, which is the probability. So x is defined here as the number of heads when 2 coins are flipped. So you can have the probability of 0 heads, 1 head, or 2 heads, right? So the probability in this case of 0 is 0.25. The probability of 1 head is 0.5. The probability of 2 heads is 0.25. And this fulfills all 3 requirements because, right, the first requirement is that a numerical random variable with number values is tied to a corresponding probability. So there's x, which is a number, 0, 1, and 2, and it corresponds to p of x, which is the probability. So we know that's good. The second requirement is the summation of p of x, the probability, is equal to 1. And as you can see here, I did the math already. 0.25 plus 0.5 plus 0.25 equals to 1. So we know that the second requirement is checked off. The third requirement, 0, or the probability of x is between 0 and 1, or it could be equal to them. And we know that 0.25 is less than 1 and greater than 0, and so is 0.5. So the third requirement is complete. So now that we know we have a probability distribution, we can also apply this by drawing a probability histogram. A probability histogram is a graph that basically shows you the probability of getting X amount of heads to the probability on the y-axis. So we have 0 at 0.25, 1 at 0.5, and 2 at 0.25. This basically shows the same thing as the data table. It's just another way of writing it. Now let's go to example 2, test mistakes. Let's just see if this is a probability distribution. So X is defined as the ways a student messed up. And the first reason is a round-off error. Second reason, missed deadline. Third reason, use normal CDF instead of inverse normal. Oh, I do that one a lot. Fourth is added instead of subtract. Oh man, that one's really painful. Yeah, these are all really common errors, but do they satisfy the rules? So the first rule is that x is, what is it, a random numerical value with number of values tied to the probability. Unfortunately, these are not random variables, random number variables. These are words, and words are categorical, so they're not number values. So the first rule is wrong, or is not there, requirement. The second rule is that the probabilities, the sum of the probabilities, right, equal to 1 or 1.01 or 0.999. But as you can see here, I did the math. The probabilities equal, when summed up, equal to 6.98, which is greater than 1, so the second requirement fails. The third requirement, the probability of each x value is between 0 and 1, or it can be equal to 0 and 1. In this case, we have two values that are greater than 1, the 4.20 and the 1.76. The 0.33 is okay, and the 0.69 is okay. But still, these two variables are greater than 1, so the third requirement does not fit. So this second example is not probability distribution. Not a probability distribution. Let's go through the probability distribution parameters. So there are three main parameters that you'll use. The first one being mu, which is the weird looking u, which equals to the summation of x times p of x, and that is the mean. And then you have what's under mu is the sigma squared, which is the summation of the probability times x minus mu squared, and that gives you the variance. So you can actually think of this as s squared. It's the same thing, just as population, basically. And underneath that you have sigma, which equals the square root of summation probabilities times x minus mu squared. And this is actually the square root version of variance, because the definition of standard deviation, or rather variance, actually is the square of standard deviation. So to take the standard deviation from a variance, you have to square root it. Okay, and let's go over the expected value. Expected value, which is denoted by the letter E up in the top left here, is an average value expected if trials run indefinitely. So, you have a test, the test goes indefinitely. The average value, which is the mean, which is mu. So actually, the average value is the expected value. So in of course formula form, that would be summation x times p of x, the probability. And so expected value is the same thing as mu, as we talked about right here. Same thing as E. Now let's go over example 3. Find the mean standard deviation and variance, mu, sigma squared, of a coin toss probability distribution. So using the values we got from the coin toss above, which is 0, 1, and 2 heads, let's see, the number x being the number of heads, p of x being the probability of getting heads, of getting those number of heads, and mu, which is the mean, and we have variance off to the far right corner. So what we can do, you can pause this and try to figure out how I did it, but how I did it is the mu is the summation of x times p of x. So I created this little section at the top here with this formula, and what I did is did this left corner, or left row, times this equals this. So 0, in this case 0 times 0.25 equals 0.00, because 0 times anything is 0. So we do that for the same thing for 1 and 2. And then likewise, likewise do that, and then you get mu equal to 0.5 plus 0.5 because we have to summation it, which is the sum. And you get 1.0. We plug that 1.0 mu into the formula at the top for variance, and then we do the same thing where we do it for each one, and we get at the end 0.25, 0, and 0.25. And this variance formula is summation x minus mu squared times probability. And in this case, if we add the probabilities together, we get 0.5. And let's just say we want to get the standard deviation. Standard deviation is sigma equals square root of variance, right? Because variance is sigma squared, and so to do that, we get square root. So the square root here of 0.5 leaves us with 0.707. So what, right? Now what? Well, basically this information tells us that when we toss 2 coins, we get an average of 1 head, a variance of 0.5 heads squared, and a standard deviation of 0.7 heads. There's also a portion called range rule of thumb, which estimates values within 2 standard deviations of the mean. This is just an estimation, so to estimate a value, if it is significant or not, basically significance is like if there's a value that is outside certain limits, then it's significant. If it's not, then it's not significant. And you can see that this value maintains between the mu minus 2 sigma, which is the lower limit, and then followed by mu plus 2 sigma, which is the upper limit. And again, mu means the mean, and sigma means standard deviation. And anything, as I said before, anything below the lower limit is significantly low. Anything above is significantly high. Now let's try this example. Example 4. Mu equals 1, sigma equals 0.7. Determine with the range of rule of thumb if 2 heads is significant. So mu minus 2 sigma 2k is 1 minus 0.7 times 2, which gives us negative 0.4 is the lower limit. Likewise, we do the addition. This gives us 2.4 as the upper limit. 2 is between negative 0.4 and 2.4, which means 2 is not significant, right? Because it is between the 2 limits, so it is not significant. And now I'm going to go over this last section a little bit here. Significant high number of successes basically means the probability of x or more is less than or equal to 0.05, then it's significantly high. If the probability x or less is less than 0.05, then it's significantly low. This is really useful for rejecting assumptions, so let's just do the last one here. Example 5, assume boy births and girl births are equally likely. Yeah, so you have 5 boys and 5 girls out of 10 births. An outcome of 2 girls and 10 births, is this significantly low? And yes, this is significantly low. 2 girls is significantly lower than 5 girls.